Hi everyone, Senan on the side, and in this video we are going to solve this search in a binary search tree. So too many searches. So you are given the root of a binary search tree and an integer val. Find the node in the BST that the node's value equals. Return the subtree rooted with that node. If such node does not exist, return null. So basically you are given a binary search tree and a value, and you need to find if that exists in your tree or not. So the logic is basically, let's say if you have a null tree, basically you have the root given to you is null, so clearly you return the null pointer because there could not be a node which has this value. Or what you can do is either try the left subtree or the right sub, fine, and you try to find the elements. And let's say, because you observe is okay, so this is a BST, right? So if I have a value of 2, right, so I'm at 4, I'll check if current node is having a value 2 or not. If this is true, that I can just return this. Now since I know the value of 2 is less than this current node 4, that means my value, if it exists, it would be on the left side of. Why? Because it's a binary search tree, so at any point of time the nodes to the left of this root 4, so every number on the left would be less than 4, and on the right every number would be greater than 4. Fine. So clearly if I know the value of my this val that is given to me, it's not equal to this and it's less than this, right? If it's less than 4, that means it is on the left. It is greater than 4, it's on the right. Now what I do is go on to this position, right? So since I did not find a node here, so I would update my this node to this node, that left child. Now I would see if the value matches this node or not. So the value is 2, this is matched, so this value 2 is same as this input that is given to us, so we return this node directly. Let's look at test case 2. We have a value of 5, so I check at 4. Okay, so is 4 is this node 4 has a value of 5? Clearly it cannot be the case because I'm just referring this node with a value of 4, so that cannot be. So what I do, if the value of 5 exists in this binary search tree, it would be on the right side of this node 4. So what I do is I go to 7. Okay, I see 7, I see the value is 5, right? So I know this is not the same, 7 is not equal to 5. Now what I do, since the value of 5 is less than 7, I move to the left child of this 7. So I reach this hypothetical null node, and since this is null node, that means I am not to find this in my binary search tree, and therefore I would return this null node. Now let's look at the implementation. You are given the root and its value. What I do is I check if this root is null, I just return the null point, fine. Otherwise what I do is I check, or rather than checking, I assign this to temp. Basically if you don't have this, this would anyways work, means if root is null, temp would be null, and if temp is null, you won't go into the while loop, and in the end you would return the null pointer. So let's remove that. So first of all, you create a pointer to this root. You don't want to modify the root, right? You create a. Now what I do is I say why temporary is not null, so that means I am at a node. So what I do, I check what is the node val, check the node at the value at this temporary node. Now if this is equal to our given constraint, this val, so that means I have found my solution and I just return that node. Otherwise, if node value is less than val, if node value is less than val, or the val is greater than the node val, that means this value, if present, would be on the right side of this node. So what I do is I assign this temp to right child. If that is not the case, it's not equal, val is not greater than node val, that means val is less than node val. That means if a value exists, it would exist on the left side of this. So what I do is I assign the temp to the left of temp. Now I do this till the time temp is not null, and I in the end return null pointer because I was not able to find it. And if I did at some point of time back, so I would just return this value. So this was a easy problem. Basically your search space is reducing by 2 every time. You're not searching the whole node, so the time complexity would be the height. In the worst case, it could be the maximum height of a binary search tree, and that would be log n. And the space complexity is again constant because we are not storing an array or something like that, a single pointer temp, and we are just updating that single pointer regardless of the size of them. So yep, that was the whole video. It is quite straightforward, it's an easy problem, and yep, thanks for watching, and I'll see you in the next video.